Swayam Prabha. Digital India. Educated India.
Hello all. So welcome to Astrochemistry. This is lecture 30. Now in the previous lecture, we were looking at what waves and particles were. We saw that because I had told you that earlier light was described as a particle until about 1700s, and then subsequently, by around 1900, it was firmly thought to be a wave. What is the rationale? The rationale was that light exhibited the properties that the waves would. For example, it would undergo interference, and then it could diffract, etc., etc. Undergo several things that were representative of the properties of a wave. But earlier on, it was thought to be a particle. Okay, right? And we saw how different, the waves and particles themselves were, right? For example, the most prominent one being that during the motion, right? While a wave moves, only energy is transferred. But then whereas a particle moves, both the energy and mass are transferred. And we also saw significant differences in terms of, how the number can be uniquely defined, the number of particles in one case, whereas the number of waves cannot be because of the phenomenon of interference, so on and so forth. Is that fine? But see, the whole discourse, right? The whole discourse about the waves, particles, and their description leads us to a very important point. It is that, look at how science has progressed. Okay. Now, from the initial idea that wave was a particle, until like around 1900, when wave was thought to be a wave, right? It is experiments. Experiments guided the transformation in our theory. What was initially thought to be a particle based on some experiments, right? The simple reflection of light, etc., was subsequently, changed. This tells us that our understanding of science, is fluid, and as more data and as our perception and our ability to understand this data change, our notion of the concepts also change eventually. Now we shall be looking at one more of these game changers in this class. Okay. Now, which again goes back to how the distinctive ideas of particles and waves are coherently brought together to describe what is called as light as we know it today. The problem, back in 1900, right, was that of what is called as a black body radiation. I mean, it is not that you all have not seen this before, right? You must have definitely seen this phrase in your thermodynamics and physics and in various contexts, in the beginning of quantum chemistry, etc., etc. Okay. However, this problem, right, this black body radiation problem was a major game changer in our understanding of physics and chemistry and has tremendous applications even in an applied science such as astrochemistry. We shall soon see why. Okay. The problem is as follows. So, what is this black body to begin with? Now, a black body is nothing but an ideal substance, okay, right? So, I'm just going to call black body as BB, okay, just a short form. So, a black body is nothing but an ideal substance. In other words, it does not exist in reality, okay, right? An ideal substance. We used to model, okay, we used to model the phenomena of radiation, okay? It's an ideal substance which we use for modeling purposes, okay, which absorbs all light, all light thrown at it. I'm going to be using a colloquial phrase, okay, all light shown at it, all light it receives and emits all of the light back. Now clearly, this can only be an ideal substance. It cannot be a realistic substance because that whenever you absorb light, as in any substance absorbs light, what happens? Some amount of it is going to be reflected back. Some amount of it is going to be absorbed by the molecules, present in the surface of the object, okay, right? So it won't even absorb all light in the first place. So a black body is expected to first absorb all light, and it also emits back. Even while emission, right? Even while emission, because the molecules, the internal structure of the stuff, right, the object can always eat away some light. Not all light is in the first place going to get absorbed, and if at all it absorbs all light, right, excluding scattering, etc., then it has to emit back all light. Okay, so no such substance exists in the world, but you can come close enough. Okay, you can come close enough to some substances which can mimic a black body to a great extent, but are not exact black bodies. Some of these examples include, the sun is one example. Okay, right? But then the sun has an atmosphere of gases, right? Which is what we saw in this astrochemistry course. All the potassium and then the sodium, etc., from sun, they're all part of the atmosphere of sun, and that's why you could even see the Fraunhofer lines, in a few lectures earlier. Okay, so the sun is an example of a black body, and there is one particular isotope of carbon, not isotope, an allotrope of carbon called as carbon black, which is said to approximately absorb close to more than 99% of the light it receives. Okay, so these are two examples of substances which are very close to being a black body. But nonetheless, in physics and chemistry, okay, we always start with ideal substances because the mathematical modeling involved is much easier. Okay, right? And subsequently, whatever deviations there are, we can introduce them later on from the ideal substance to what is actually encountered in experiments. Okay, so this is the problem. There exists something called as a black body. Okay, right? And if you plot the amount of energy that a black body radiates, okay, right, or it emits, the amount of energy the black body emits, per unit volume. Okay, so I'm going to call this rho, or like joule per meter cube. Okay, right? This is the amount of energy per unit volume, right, of that black body, which is emitted, right, versus the frequency. Okay, right, versus the frequency. You're expecting, an experimental curve of this form. It, of course, the exact shape of the curve depends on the temperature also. And let's say that, this is approximately at 5000 Kelvin. I mean, temperature is not unimaginable, right, when we're dealing with the sun, etc. Okay, right? Let's say that, the temperature of the black body is around 5000 Kelvin, 5000 or 6000 Kelvin approximately. Okay, right? And as a plot of the energy density versus the frequency of light, right, you get some such plot. Okay, notice that this is going to be asymptotic. Okay, it approaches zero, but it is not exactly zero at very high frequencies. Now this was the experimental plot obtained. Now the problem in 1900s, okay, early 1900s, let's say around late 1800s or early part of 19th century or 20th century, that is 1900s, okay, was that based on the known physics of that day, the theoretical curve obtained was something like this. Okay, I'll draw it even better. It started off with some agreement. And then there is this huge divergence. Okay, this is theory. The theory of light, okay, which understands light to be a wave, okay, right? That leads to a curve like this. Whereas the experimental curve, is like this, right? Now this is at 6000 Kelvin. At different temperatures, the key point is that, at different temperatures, I don't really worry about the temperature dependence for our purpose, but I'll discuss some bit of it in the tutorials. Okay. Now at different temperatures, shape of experimental curve will change. Please note this. Okay. Shape of experimental curve will change. Okay. But there will always be a discrepancy between theory and experiment. Okay. But theory versus experiment. Experiment, I'm writing in shorthand as EXPT. Okay, right? Discrepancy at all temperatures for higher frequencies. If you notice here, right? At lower frequency, there is some agreement between the theoretical curve and then the experimentally obtained curve. But at higher frequencies, the difference is becoming larger and larger. Okay, are we all good with the situation? So this is the famous black body problem in 1900s. In other words, experimentally, well, I have a well-defined maximum and then the curve goes down. That makes sense. But in some region, at some region, the amount of energy emitted by the black body, okay, right, at some frequencies, right, it doesn't come down at all. It just keeps going up. In other words, there should be no darkness, if you think about it, right? If something keeps emitting more and more and more and more energy, right, there should be no darkness at all, right? That was the big problem, facing physicists, okay, right, back in the late 1800s. Are we clear about the problem? Now, how to explain this? In fact, the same situation, could be mathematically described as follows. The physical picture in the mathematical model corresponding to this graph is as follows. Now, the average, so what's happening? Light is shown atop a black body or to a black body. Okay, a black body receives some light. A black body is receiving some amount of light. Now, after this light is received, the black body contains atoms, right? Everything is made up of atoms and molecules. So that's a clear picture we have. Okay, right? So the atoms in the black bodies, they get excited and minor atomic oscillations are generated. Okay, this is the picture. So black body radiation. Picture. A. The physical picture and the mathematical model. I'll come to the math very soon. Okay. So light, which is received by black body, right, causes small atomic oscillations. All right, small atomic oscillations in the black body. Okay, now used on the known physics. Okay, right? Not used on, based on the known physics in approximately 1900s. Okay, right? Based on the known physics of 1900s, it was shown that. It was shown, not shown, it was thought, okay, right? Because we're talking about the theoretical aspect, okay? It was thought that the average energy of each of these small atomic oscillation, okay? The average energy of each of these atomic oscillations was proportional to nu square kBt. What is kb? We've seen this constant before in this course. It's R by Na, okay, right? It is nothing but the Boltzmann constant. Recall, probably in our discussion on the differences between interstellar medium and Earth, right? We introduced this notion called as the Boltzmann constant, okay, which is nothing but R by Na. I'll write it in the next page, okay. With units of joule per Kelvin, right? Because this is R is joule per Kelvin per mole, PV equals nRT, and Na is per mole. Okay, Na is the Avogadro number. All right, unit is going to be like the per mole is going to be getting cancelled, and so the net unit is going to be joule per Kelvin, and its value is also going to be approximately in SI units. This number is what, 8.314 something in SI units, and this is 6.0. So 6 divided by 8.3, 6 ones are 6. You have 2 and then 0, 1.3. So approximately this is going to be 1.3. And this is 10 to the power 23 here. This goes up times 10 to the power minus 23 joule per Kelvin. Okay, right? So this is your Boltzmann constant. Okay, this is Boltzmann constant, and this is the temperature. Now you can see that based on the known physics of the day, because the E average, right? This is based on what is called as the theorem of equipartition theorem. Okay, which gives the amount of energy associated with each type of motion for the molecules. Okay. Let us not go into too much details because then it will be a full-fledged, a lecture on black body radiation itself. which to understand the complete picture, giving you all the equations and the physical picture, it would take me probably 4 or 5 hours of mere black body radiation itself. Okay, but don't lose sight of the bigger picture. We are seeing and understanding black body picture to understand astrochemistry. Okay, so as part of it, I'll give you a succinct presentation. Okay, and only the summary. So the summary is that the average energy is proportional to nu square, Kb is a constant, and temperature. So for any given temperature, right, your E average is proportional to nu square. That is of course reflected in this curve, right? Y equals x square. It keeps going up and up and up, right? It doesn't go up, come down at all. Okay, this situation is what is called as the ultraviolet catastrophe, because the frequency ranges, where it actually reaches this, it keeps going up and up, happens in the ultraviolet range. Okay, so your E average was proportional to nu square, and that sort of explains why the theoretical curve never goes down. Okay, are we clear? So the physical picture is that tiny atomic oscillations are created in the atoms of the black body, and they emit, right? They emit energy. The average energy of each oscillation is proportional to nu square. At any given temperature, it is proportional to nu square and Kb. Don't worry about the exact constant right now. Are we good? Okay, now this was the picture and this is the problem. Now, this person, this visionary person called as Max Planck, so Max Planck, approximately in around the year 1899 or 1900, I believe, okay, right, was trying to solve this problem. Now, the way Max Planck approached it was that, now see, before looking at Max Planck's approach, you see that this nu, right, the frequency of the incident light can also be anything, correct? Light is a wave, and wave can be of any frequency. A few lectures, earlier in the same course, we were discussing about the electromagnetic spectrum, right? And we saw that the spectrum ranged all the way from the radio waves to the X-ray, gamma rays, etc. on that side, correct? Now, the nu here, that is, the frequency of wave can therefore be continuous. In other words, the value of the frequency need not be, only limited to certain values. Are we good? Do you folks understand what I'm talking about? A priori, Max Planck was working, okay, right, in the days when it is widely understood, it was widely understood nu, right, can be continuous from 0. I mean, we're talking about the numerical value, not talking about the units, okay, right, to any positive number. I have written it way below in the board, so I'll say what I've written here, because the handwriting may be bad, and also I've written way down. So Max Planck was working in those days when it was understood that nu, that is the frequency, can be continuous. In other words, there are no discontinuities in the graph, okay, right? It is continuous all the way starting from 0 to any large positive number, okay? So nu can be continuous from 0 to any positive number, okay? Please note it, right? It makes sense, right? Light is a wave, and wave can come in any frequency, right? So, and there need not be any breaks or disruptions to the continuity. Are we clear, right? So then Max Planck, came up with the idea. Now, notice this. You look at this graph here, you look at the graph and you say that, hey, for lower frequencies, okay, so for lower frequencies, that is like for nu, the lower range, of course, I haven't given you the scale here, okay, so don't worry about the exact scale, okay, but for lower frequencies, there is very good matching, there is very good corroboration between the theory and experiment. The experimentally obtained curve matches very well with the theoretical curve, right? Theory is based on the physics of the day, and experiment is based on the experiments done, okay? So the problem arises only at higher frequencies. So until a small range of frequencies, the curves match. Only at higher frequencies, you see that, the discrepancy, right, in the theoretical and the observed curve becomes more and more. And at some point, the theoretical curve never comes down at all, whereas the experimental curve comes down. So Max Planck thought, okay, so how do I solve this problem? This curve which is just keeping on going up and up and up, this has to be brought down somehow. So there must be some way I must be able to do this. This was Max Planck's idea, and you know what he did? He did something very profound, which can undeniably be stated as the foundation stone for modern spectroscopy, and in so many ways even modern astrochemistry. Okay, and Max Planck proposed that look at the phrase I'm using. I'm not saying Max Planck derived, okay? I'm using that Max Planck proposed. What is the difference between deriving something and proposing something? Well, deriving something is when you start off with some starting point which is regarded as like being fundamental. You start off from a starting point that is well regarded and is fundamentally accepted by all, and then you start from there and you keep going on. In other words, you start from F equals ma, and then you derive other equations of motion, etc., etc. But the starting point F equals ma is well accepted in classical mechanics. Okay, that would be a derivation. A proposal would be that let's propose that F equals ma. That itself is a proposal in the first place. Okay, you get me? So Max Planck did not derive. I want to intentionally emphasize and slow down and repeat once again. Max Planck did not derive. What did he do instead? He proposed, okay? He proposed that, okay, so, the light emitted by these oscillations, it cannot be of all frequencies, not all frequencies, The point is the continuity of the frequency range, okay, right? That need not be the case, okay? Let's say that light only such light is emitted, okay? Only such light is emitted which obeys E equals NH nu. Okay, right? Now your E is in your energy in joules. Okay, well, N is some integer. Okay, N is some integers, taking the form like greater than 0. 1, 2, 3, blah, blah, blah. Okay, so your nu is going to be in frequency. So your nu is going to be in frequency, that is going to be per second. Okay, right? And your h is the Planck constant. Now, based on this was a constant he proposed. Okay, right? Because it is a number, it has like no dimensions of its own. So your h is going to be, energy is going to be joule, and this is per second. So joules per second. So that's going to make it joule seconds. Okay, so this was a constant he proposed. It was some constant, but the key idea is that only such light is emitted back which obeys this law. In other words, what Planck did was, effectively he said that not all frequencies are permissible, right? Only discrete values of frequencies are permitted. Okay, right? Discrete allowed. So only discrete values of the frequency are allowed. Okay, not all. What is the basis? Well, he did not give any basis. It was, you can think about it as a desperate situation, but a genius solution. Okay, a genius proposal to sort a desperate situation. Hey, I have a curve which is like going up and up and up, right? I have to bring it down. Okay. So as one way of solving the problem, let me just assume that not all frequencies of light can be emitted back. Are we good? I mean, not all frequencies of light can be emitted back, and because it's a black body, not all frequencies of light are also absorbed. Okay, only light whose frequencies correspond to the energy equation this way. See, always recall that the energy of a light wave is somehow associated with its frequency. Okay, now for example, I have deleted it, but even based on the known physics of the day, I had written that E average was proportional to nu square, right? So it had to be some form, right? So the physics of the day back in the day, based on equipartition theorem, they said that the E average of the light is going to be proportional to nu square. Okay, so energy can be somehow associated with frequency. Now Planck came up, again I use the word came up, did not derive. Okay, Planck came up with this expression E equals nh nu, right, to associate frequency with energy, and he said that only those values can be emitted back by the atomic oscillations. Are we clear? The atomic oscillations which are responsible for the emission of light, right, back from a black body, they can only be, light of this form. Now, because it's a black body and because it emits back all the light, okay, right, the incident light, that is, the light received by the black body, can also be only of this form. In other words, a revolutionary idea was created by Max Planck. He said that, hey, the frequency range, okay, right, the frequency range of light, it need not be continuous. I can only have discrete values. Now, using this idea, okay, right, using this particular idea, I will delete this part, I'll keep the curve. Okay, so using this idea, Planck said that the E average, that is, the average energy associated with each oscillation, recall that it was proportional to nu square kBt in the earlier case, based on the known physics of that day. Okay, right? That was the value we were discussing. Planck proposed a different expression using this idea. I'm skipping the math, okay, not skipping the exact derivation, because like I said earlier, that would take at least 4 or 5 classes. It's not that important for the class in astrochemistry, but the conclusions are, okay. So I'm going to give you the gist of what you obtained. So using this idea, and after skipping a lot of steps, okay, we get the E average to be, of the oscillation to be, something like h nu divided by e to the power h nu by kBt minus 1. All right. So this was the expression that he derived as the average energy, right, of each oscillation, each atomic oscillation. Using this idea, what is in between this and this? There are lots of steps. We have skipped it intentionally for the purpose of time. Okay. So now what did this expression do? That's very interesting. Okay. Take a look at this expression. Now E average is h nu by kBt minus 1. Correct? Now let's take, consider the denominator. Okay. Right? Now this is of the form e to the power ax. Right? So the denominator is of the form e to the power ax minus 1. All right. Now, let's say, you're talking about like small values of h, you take large values of h nu. Okay. Let's say, at large values of nu. Forget, like what h is now. Okay. H is just some constant. Okay. Now, for large values of h nu, if you look at the denominator, you understand two things. Based on the form of y equals e to the power x, right? It starts off slowly, but then it goes rapidly rises. That's why it's an exponential function, right? So at large values of nu, you understand that the denominator, that is e to the power h nu by kBt minus 1, is much, much greater, right? The denominator is much, much greater than the numerator. Are we clear? Right? So the denominator is much, much greater than the numerator. So the energy, right? The energies of such oscillators are going to be negligibly small. Correct? So because of the exponential nature of the function, you can work on the exact graphs, okay, right? At any given temperature, right? For large values of nu, right? You see that this is much greater than this. So therefore, this is going to be small. As a result, what happens? What happens is that the curve which was going up can actually be made to come down. So what did Planck do? Based on his revolutionary proposal, without knowing why it could be made, okay, he came up with an expression. He came up with some expression, and using this expression, he was able to account for, the experimental curve, right? By kind of proposing a revolutionary idea that the frequency need not be continuous. All right. Now, We will continue with the same concept in the next lecture. Okay, right? For now, the summary of this lecture is that black body radiation presented an interesting problem, and Planck came up with a revolutionary solution for it. More in the next lecture. Thank you.